Well, so good morning, everyone. My name is Leo. I'm the founder and the research leader of MigaLabs. Thank you for coming. Today, I'm going to talk about the first 100 days of Fusaka and the future of PeerDAS. So just to do a small recap of what is PeerDAS. So this is a solution to avoid downloading the whole blob data. So we know that on the rollup-centric scaling roadmap, we have now blobs of data where rollups can put everything, all the data they need in order to have inherited the security of layer 1. And so we have a number of blobs that are submitted to the L1 at every slot. And the idea is that we want to scale this number of blobs so that the rollups can put more and more data as we try to scale, but we don't want the nodes in the layer 1 to need to download all the data from the blobs. So for that, what we are trying to do is the following thing, which is we extend the data with Rich-Solomon encoding, and instead of downloading the whole data set, you only download part of it. In particular, we download only a certain number of columns. So I believe today, any full node in the network is downloading 4 columns. If you are a super node, that means you are running many validators on your node, or for example, you are a block explorer and you want to have all the data, then you are what is called a super node, and then you download all the columns and you download the full data. But the rest of the nodes do not need to download all the data. They only download a number of columns. So the black columns here are the ones that, for example, that you will be downloading. And so that is basically Fusaka, okay? That is in a nutshell what Fusaka is, PeerDAS is introducing in the Fusaka hard fork. Now, the purpose of this talk is to explain and to show what has happening since the Fusaka hard fork and the BPOs. So the Fusaka hard fork happened in December 3rd of 2025, so last year, a few months ago. And the two small dots that you see are BPO1 and BPO2 that happened in December and at the beginning of January. And so 40 days after that, I wrote a blog post showing the state of the network and in particular the blobs after 40 days of the Fusaka hard fork. And today I'm going to do an update on that blog post. So first I'm going to present what I already published in that blog post, and then I'm going to talk about the update today. So this is a busy figure. Let me explain. What you see here on the red line is the number of miss blocks per day. Okay, so every single dot in the x-axis is a day, and then the red line shows you how many blocks were missed that day, and then the box plot, it shows you more or less the average and the quartiles of the number of blobs that were published per slot. Okay, so what you see is before the Fusaka hard fork, we were at a very steady, in average, 6 blobs per slot, with some variance, but the mean was very stable at 6. And then after the first BPO, we increased that to the average was supposed to be 9 blobs per slot, and the maximum 15. Okay, but what we saw that happened is that the mean number of blobs per slot decreased actually to 5, and then after that, with the second BPO, that further decreased to 4 blobs per slot. So, in other words, we increased the capacity, but somehow we are not filling that capacity. That layers 2 are not really using all the space that they have, and so the question is why, right? And so that's one observation. And the second observation, so yeah, here you see the number of the distribution of the number of blobs per slot after 40 days of the Fusaka hard fork, and you see that slots with 16 or more BPOs are extremely rare. There are less than 0.1% of slots that actually are in this category. Okay, so this is strange. I mean, we were thinking that the purpose of extending the number of blobs is so that we could, fulfill that capacity and help scaling, in particular for layer 2s. But that's not what we see. Not what we see here. And we also looked at the number of miss slot after a slot with a certain number of blobs. Okay, so let me rephrase that. Here, what you see is when we observed that there was a miss block, we check what was the number of blobs in the preceding slot to see if that somehow has some influence on whether the next slot is going to be miss or not. And so we normalize that by the number of slots with a certain number of blobs. And what we see here is that after a slot with 16 or more blobs, the likelihood of having a miss block in the next slot is over 3 times higher than just a slot with a low number of blobs. Okay, so that's bad news, because that means that if we really reach that capacity, the network somehow becomes saturated, or the node becomes saturated, and then we are not really in a good position for publishing the next block, and then sometimes you will have missed blocks because of this reason. So that was kind of an alarming discovery at the time. So that was 40 days after the Fusaka hard fork. And now I'm going to present the second checkpoint. So this is 100 days after the Fusaka hard fork, and to see if we still see the same findings or if the situation has improved or not. So this is the same figure that I presented previously. You see that the number of missed blocks is quite stable. But we also see that the mean number of blobs per slot is still quite low. It's still at around 4, and actually even decreasing a little bit in the last few days. And we are nowhere near close to the 15 blobs per slot that we were supposed to be. Okay, so in this context, this has not improved so far. Okay, so why is that? There might be a number of reasons. First, we are in a bear market. That could be one of the reasons. Now, we also increased the gas in the layer 1 from 45 million to 60 million. Now, also, we have much lower gas fees on layer 1. So maybe people are using more the layer 1 than the layer 2s. So all of these reasons could be, could play a role in what we observe in this figure. The expectation is that hopefully layer 2s at some point will start filling that capacity, and we reach the levels that we were expecting. Now, but this is also a bad thing, because if we are not playing at that level of capacity in a sustained basis, then we don't really know if the network can handle it. We really want to have, for example, a month where the mean number of blobs per slot was constantly 15, maybe with many cases of more than 16 blobs per slot, to really know that we are actually, that the network can handle it, that the nodes can handle it, and that we can sustain that in order to then further increase for the next BPO. Okay? But since at this moment we are not reaching that capacity, we really don't know. We don't have the certainty that we can move further on the number of blobs, because, yeah, we are not playing at that level. Now, regarding the other discovery, again, you can see that the number of slots with 16 or more blobs is still very low, so that has not improved. And then regarding the missed slots, after a certain number of blobs, now the situation has improved. And that is the good news of this, is that after 100 days, we do see that the probability of missing a block is the same regardless of how many blobs were published in the previous slots. Okay? So there is no correlation between high number of blobs and missed blocks. Okay? So this is an improvement. These are the good news of the talk. And so that was solved, apparently. And so this is good. Now, in a nutshell, what I have said today, regarding the first 100 days of Fusaka is there are good news. First, we now see that there is no correlation between high number of blobs and missed blocks. That is good news. The not great news is that we are still not even close to reach the target throughput that we expected with the BPOs, and therefore we don't really know if the network and the nodes can handle this sustained high throughput. Okay, so these are the two, basically, if you had to remember something from this talk, those are the two things that you should remember. Now, if we want to talk about the future of PeerDAS, there are several improvements that are coming. One of those is cell-level dissemination. So this is important because we want to reconstruct data. But today, to reconstruct data, you need at least half of the row, basically. But the only way you will have half of the row is if you have actually half of the columns, right? And so that means basically the only nodes that can reconstruct in the network are super nodes, okay? So that's bad because then we are relying heavily on super nodes. And that's not great for decentralization. So cell-level dissemination is a step forward in that if we can disseminate cells or particular cells on the columns, then we don't need to have basically the entire data set in order to recreate the other half or to reseed the network, right? So this is an improvement and is already on progress. I think several of the clients have already implementations working on this, and it's probably gonna come in the coming months. We will have cell-level dissemination. So this is one of the important things. Now, I will argue that it's important also to move to two-dimensional PeerDAS. Now, this is a little bit controversial, but not much, I think. But yeah, some people say that we don't need to go there yet, that with one-dimensional PeerDAS, we are okay. I think we will be okay up to some extent. I think if we keep increasing the number of blobs, disseminating columns and sampling columns instead of sampling cells is not really optimal. I think the two-dimensional scheme, which it doesn't need to be so fully two-dimensional, we can actually extend vertically just a number of rows, and that will already help us to reconstruct data much easily, and will make the whole scheme much more robust. And also for sampling, if you are sampling cells instead of sampling columns, you will be reducing the bandwidth on the network. And so that's also another benefit. So I think it's important to keep this in mind. If we can move towards something that is perhaps not full DAS yet, but at least partially two-dimensional, I think it would be good for the network. And finally, more further into the future, we are looking at post-quantum blobs. So what that means is that right now for disseminating the blobs, we rely on KCG commitments in order to make sure that when you receive a cell from any node in the network, you can easily know that this is actually part of the polynomial of the original blob. And the problem is that KCG commitments can be broken with quantum computers. And so we cannot rely on KCG commitments in the future after quantum computers are here. And so the question is, what can we use? And so there is a lot of research already in post-quantum signatures using lattice-based technology and so on and so forth. But the problem is that when you use those techniques and you recreate the cells, then the proof that you generate is going to be different than the original proof that was disseminated. And this is a problem because then you cannot really reseed these reconstructed cells into the network. So basically, at this point, we have really no solution on how to succeed to have blobs in a post-quantum world. But the good news is that there is a team that is very heavily working on it, and we hope that by the time quantum computers reach us, we will have already a working solution. So yeah, that was my talk on the future of PeerDAS. If you have questions, I'll be happy to answer. Thank you.